Hello, I'm Pete Zielinski, Editor-in-Chief of Modern Machine Shop Magazine. Welcome to today's webinar titled The Truth Behind High-Efficiency Toolpaths, brought to you by SolidCAM. Our speaker is Ken Merritt, Director of Partner Projects with SolidCAM, and Ken is at the East Tech trade show right now. You might hear some trade show noise in the background while he speaks. As Ken is talking today, as he's giving the presentation, please ask questions. You can do that using the Q&A section at the right of your screen. We'll see the questions entered in that box, and at the end of the talk, we'll answer as many as we can. Ken, if you're ready, please begin.
Okay, I am ready.
Today we want to talk to you about SolidCAM's iMachining 2D and iMachining 3D modules, and how they compare to other high-efficiency toolpaths from various other CAM systems. The first benefit is that SolidCAM runs directly inside the user interface of SolidWorks and Inventor, taking advantage of the solid model faces and edges to give you fully associated CAM. iMachining also runs as an integrated, best-in-class roughing option, fully associative in the Siemens NX CAM. iMachining has two independent modules: the Intelligent Toolpath Generator, or the algorithm, which is fed by the iMachining Technology Wizard. The wizard automatically provides the parameters necessary for the iMachining algorithm to calculate the world's most effective morphing spiral toolpaths, supported with D-slot trochoidal motion to optimize regionalization with the most effective repositioning known to CAM. iMachining has several unique patent claims. The cutting angle is managed between 10 degrees minimum and 80 degrees maximum angle to support our morphing spiral motion. Feed rate is modulated according to that cutting angle to maintain a constant chip thickness, which results in a constant spindle load. As you can see here, the feed rate is changing as the cutting angle changes from 20 degrees to 50 degrees. As I mentioned before, our morphing spiral motion control that you can see here on the left is a SolidCAM patented technology and cannot be used by any other CAM company. Now, spiral efficiency separation channels that you see on the right are also another patented feature unique to iMachining. This gives us the ability to optimize long, narrow topology into more symmetrical regions where the morphing spiral can operate closer to or at the maximum cutting angle, where it's getting the best material removal rate. iMachining will always preference morphing spiral motion, whether it is an outward to inward spiral, or as is shown here, an inward to outward direction. iMachining will continue as far as possible with the morphing spiral, and then switch automatically to the D-slot trochoidal to clear obstacles so that it can again return to the morphing spiral where it's more efficient. Now, iMachining will also constantly update the remaining stock during the runtime of the algorithm so that it always knows where it's safe to move the tool during repositioning. iMachining handles remaining stock removal very well. Remember, I mentioned earlier that it's always updating the stock model with each movement of the tool. So in areas where the previous tool would not fit, the next smaller tool is driven right from the edge of the remaining stock so that there's no wasted air cuts, maximizing efficiency. Another unique feature is how iMachining handles finish passes in 2D prismatic parts. When the model radii are very near the tool radius, the tool can chatter in those corners. Well, iMachining detects these conditions and uses D-slot trochoidal motion to remove most of the stock prior to running the final contiguous pass for the wall finish, resulting in amazing surface finishes and completely eliminating all that chatter. Let's take a look at iMachining in action in some chromoly material. iMachining is really above all other systems in that it takes information from four very important categories to calculate the proper parameters throughout every move of the tool through the entire operation. This ensures that the tool is always machining under the best conditions, really running in the sweet spot. You see, with iMachining, material properties, tool characteristics, and machine kinematics are all analyzed relative to the axial depth of cut to make sure that the tool is never overloaded and the spindle load remains unbelievably constant even while performing at the highest levels. So as you can see, the iMachining technology wizard really is where the magic happens. It removes the guesswork and seamlessly integrates those four categories of information into the algorithm for the calculations that keep the tool running so smooth and with such a remarkably constant force load that even while it's at unbelievable material removal rates, the tool life actually increases. The iMachining level slider gives the user a very convenient way to set the performance level from minimum to maximum, while the wizard puts together the appropriate parameter sets for each level to drive the algorithm, making first cut success actually the standard experience. iMachining also calculates vibrational stability implications relative to the axial contact points of the tool and the rigidity of the spindle column, offering the user recommended optimal cutting depths for different conditions. Now, no other system in the market even comes remotely close to the complete solution that is SolidCAM's iMachining. We have several customer success examples showing the fantastic results that they are getting using iMachining. This titanium part at Gardner Aerospace in the UK is a great one. Now, most machinists understand that titanium is a pretty tough material and it's kind of hard on tools. Well, Gardner was machining these pockets with a 14-minute cycle time with the program coming out of CATIA. They purchased SolidCAM with iMachining and now they're able to do this pocket in just 3.5 minutes. They're actually getting much better tool life now than they ever did using CATIA's roughing solution. Another of our customers was cutting this aluminum part in 17 minutes with their previous system. And when they implemented iMachining, that cycle time came down to 6 minutes with less work-induced stress in the part. Now, that represents a 73.5-hour savings of machine cycle time over a 400-part order, while producing parts with less internal stress that will perform better in the field of service. Whether it's soft materials like aluminum, where we really need to consider the induced forces along with the cycle time, or if it's tough to cut materials like this titanium part, the savings that our customers are realizing using iMachining are staggering. Again, this example here demonstrates an 80% reduction in cycle time with iMachining. iMachining 3D can provide savings even more exciting than the 2D mode, pushing the limits with even up to 90% savings being realized in certain cases. Now, iMachining's 3D module is really designed for both 3D surfaced parts as well as 2D prismatic parts. You see, iMachining's 3D is using the proven technology of iMachining 2D to get the maximum efficiency, optimizing each Z-level step. We're actually analyzing the entire model, and the system is computing the best case scenario for optimal ordering over the entire process. And we're taking full depth step downs where applicable, achieving maximum material removal rates. Now, I want you to notice how quickly iMachining 3D clears this pocket in heat-treated steel in this next video. iMachining 3D not only produces extreme savings in roughing cycle times, but by using step-up scallop height calculations, it can leave the model in a true pre-finish condition, ready for the final finishing operations. You see, these Z-steps are calculated based on surface inclination angle to achieve a constant scallop height, further contributing to stabilizing the force load on the finished toolpath, even though that toolpath comes after iMachining. This automatic scallop control basically obsoletes the need for a semi-finish cut with a ball nose tool to prep for the final finishing toolpaths. Depending on the model, this can result in dramatic overall process time savings in addition to the roughing cycle time savings. We also check the updated stock against the holder and automatically adjust the toolpaths so that you can still machine most of the model with shorter tool extensions. iMachining 3D increases chip thickness and cutting angle for shallow step-up cuts to maintain constant force on the tool and spindle when the depth of cut decreases in the shallow staircases. As you will see in this next video, iMachining eliminates time-wasting back and forth repositioning moves. Notice how effective that tool was working. Our regional optimization technology eliminates repetitive long repositioning and retract moves, as is clearly shown in this next video, where we're using the updated 3D stock to eliminate air cuts. It bears repeating that iMachining automatically adjusts for the conditions of a Z-step, maximizing the performance while maintaining a constant force load on the tool and the spindle. iMachining 2D leaves the ordering and depth control to the user, allowing them to choose exactly how they want to machine the part and in what order. iMachining 3D provides a powerful automation technology, analyzing the model and providing optimized pocket depth recognition and regional ordering control. This makes programming complex prismatic parts very easy. SolidCAM automatically controls entry and exit lead moves for each cut, resulting in smooth motion that is extremely efficient and contributes to greater tool life and machine life. Hey, imagine how tough it would be to have to figure out which feeds and speeds to use with which axial depth of cut for what cutting angle range in any specific material on a particular machine with a given tool, and then have to figure out how to adjust all that on the fly as the axial depth of cut changes with the step-up scallop control. Well, the patented iMachining technology wizard eliminates that challenge by automatically figuring out each of those items and more, making programming as simple as picking the geometry, choosing the tool, and setting the machining level slider control to the desired performance position. iMachining then computes all of the necessary parameters for each changing condition of the cut throughout the whole toolpath operation. iMachining's patented technologies are powerful features that keep it leading the pack when it comes to bulk material removal. The cycle efficiency, coupled with seriously extended tool and machine life and the ease of programming, builds a reputation that no other CAM system can touch. And doing this right inside today's most popular solid modeling CAD systems makes SolidCAM the true leader in integrated CAM. The real story always comes from customer experience, and these examples show dramatic cycle efficiency improvements over traditional toolpath styles. These next two videos show how iMachining is also being implemented with XC motion for advanced mill turn machines as well as roughing prep for 5-axis simultaneous tool motion in even the most complex parts. Minimizing the force load on the tool is the most important factor determining tool life. But just like it helps the tool last longer, it's also extremely important to the machine and spindle. The smooth motion control of iMachining means that the servos and the drive components are not being impacted by shock and stress. You see, SolidCAM's iMachining 2D and 3D default settings produce minimal spindle loads and ensure that the wear on your CNC machine will be almost non-existent when compared to non-iMachining toolpath generators. You know, your machine can be one of your most important investments. It's nice to know that iMachining has got your back when it comes to protecting the things that matter to you. Companies like Hermele and Makino have discovered that iMachining drives their machines at maximum performance levels while ensuring that the forces applied to the machine and the spindle are less than any other CAM system on the market. So how does iMachining compare to systems like volume mill, dynamic mill, profit milling, and others? Well, first, iMachining is the only system that is focused on managing constant cutting force. That in and of itself is a huge difference. Force stabilization is the key to performance and tool life, as well as reduction in work-induced stresses. As you can see in these charts, no one else supports the key factors necessary for force stabilization and supreme performance. Variable cutting angle range, feed modulation, morphed spiral motion control, managing thin wall conditions. These are all very, very important technologies. The system has to be comfortable to use also. Nobody else offers a technology wizard to figure out all the complicated combinations of parameters that need to be set to make all this work. You have to be able to learn the system in a reasonable time and be effective with it. Reduced cycle times means increased profits. Being able to be successful right out of the box with complete processes that reduce programming time means that you're not wasting time on trial and error mode. Our customers love iMachining. You will too. So how does SolidCAM's iMachining compare with what they call high feed milling? Let's take a look. This image shows the in-process result of a toolpath that is generally referred to as high feed milling. The style of toolpath is based around very shallow depths of cut, using up to 80% of the diameter of the tool for radial step over, and using much higher spindle speeds and feed rates than would be used in a traditional, or what we might call an old school pocket operation. As you can see in this image, the toolpath starts at the top and works its way down to the bottom with very shallow steps, clearing out the entire area at each step. Now these toolpaths are almost always performed with inserted cutters, similar to the one shown here. You'll notice in this image that the shallow axial depth of cut ensures that the force vector on the tool is directed in a more parallel direction to the tool axis. This is what allows for the higher spindle speed and feed rates. Now typically these step downs are very small, around 25 to 40 thousandths of an inch or 0.6 to 1 millimeter. Now the chip formation for these actually transitions from chip thickening to chip thinning, which can result in some pretty serious vibration dynamics depending on the stability of the spindle column and the part mounting characteristics. This type of toolpath can, however, be pretty effective when the pocket is either extremely shallow or extremely deep. We've got a few more minutes left in this webinar, so why don't we take a little bit of a look at some of the physics behind what makes iMachining as powerful as it is. Now, one of the things that's really kind of an interesting study is what we're actually doing on CNC machines. This is a video, high-speed video, highly magnified, of a lathe insert passing through 1018 cold roll steel. Now, this chip thickness is probably in the neighborhood of 4 to 5 thousandths of an inch, okay, but you can see underneath here, it's kind of interesting, you can see the material sort of bend down and flex and come back up. That's known as material memory or elastic deformation, the ability of a material to be deformed from its natural state, but when the pressure is removed, it can return to where it was. What's going on along this line is called plastic deformation. This is actually a dislodging of the molecular structure and separating that material. This is the actual chip removal. Okay, really more of a chiseling effect, if you want to think about it that way. Now, there's a lot of energy that is imparted into this and generated from this, and that energy all has to go somewhere. Typically it goes into heat, and you see a frictional heat and so forth, creating a rise in temperature of both the part and the tool. Okay, with iMachining we change a lot of that because we're actually managing it much better. We look at the cutting edge velocity as it relates to the chip thickness, not the chip load now. Okay, the chip load is always measured out here at the 90-degree quadrant relative to the motion of the tool, and it is the thickness of the chip per flute per revolution of the tool. What we're doing is we're actually measuring the chip thickness at the cutting angle, and that's how we're controlling the feed rate in our system. And that's whether you're at a minimum angle, a maximum angle, or anywhere in between. And that really changes the way the system works. And so I want to talk a little bit about the theory of plastic deformation and the latent energy of plastic deformation. One easy way to illustrate this is with a knife on a tomato. If you take a sharp knife and you push straight down on a tomato, it will chop the tomato, but it's going to squish it or deform it when it does it, okay? But if you take that same knife and you pull it very fast across the tomato, the knife will fall through the tomato without ever deforming the tomato in any way. And that sort of illustrates, the physics are a little bit different, of course, but it illustrates for us very well the fact that we've discovered that as you increase your cutting edge velocity, you decrease the latent energy of plastic deformation for the same chip thickness. Okay, and this can be seen quite easily actually at the spindle load meter. If you're doing an iMachining toolpath and you increase the cutting edge velocity and maintain the chip thickness and the angle of engagement, you will see your spindle load meter come down. And it's kind of interesting to watch how that works. But let's talk about that as it applies to a lot of different factors here in this graph. We have the rotational velocity of the tool, meaning the velocity of the flute as it is passing through the material. We have the forward velocity of the tool, meaning its advancement along the cut line. And of course we have the minimum to maximum cutting angle, which is describing the engagement of the tool in the material. One of the things you can look at in this is you can kind of think of this segment here as the heat generation cycle of the full revolution of the tool. And so as you increase or decrease this angle, the maximum cutting angle, you are actually increasing or decreasing the duration of time through a one revolution cycle that heat is being generated, okay, and what we do with that heat. Now, the stability of the pressure vector, okay, that's this pressure direction that's on this tool, is extremely critical. And when that pressure vector is not stable, you're going to see things like harmonic vibration, okay? And one of the things, there's a lot of companies out there that are starting to study harmonic vibration in machines. For years and years they've been developing all kinds of science into the castings of CNC machines to try to dampen that vibration, all right? Well, a lot of that vibration is generated by the flute crossing this 90-degree quadrant. We'll talk about that in just a moment. But let's take a look at a traditional type of cut and see what dynamics we're dealing with in this equation that we see, okay? Most traditional toolpaths were always basically an offset racetrack pattern that the tool was following. And every time the tool changes direction, what I like to call the compression zones of the toolpath, the tool becomes completely enveloped in the material, over-engaged if you will, and we wind up in a full slot width cut where a lot of things are going on that are very negative for the tool. And so I want to talk a little bit about that too. Over here on the left hand side, we've got chip thickening going on. On the right hand side, as the flute advances through the cut, we have chip thinning. Now chip thinning is obviously better, okay, but chip thickening has a couple of things that are very detrimental to the process that we want to talk about. Number one, as the flute begins its movement and progression through this cut, the initial pressure vector on it is in direct opposition to the tool direction of motion. So this adds to a linear force or a bending force against that tool. Remember we talked earlier about traditional tool paths is concentrated all down there at the end of the tool, okay? And this is one of the contributing factors to that. As the flute advances, that pressure vector moves with it, and up here at the 90-degree quadrant, it's pushing perpendicular to the path of the tool and causing deflection. One of the reasons we have to come back and do a spring pass a lot of times. Now, one of the very, very bad things that happens is pressure vector oscillation. Like I said, it causes that, what we know as harmonic vibration. That usually happens right here at the quadrant as the flute is passing that quadrant. And let's talk a little bit about the physics of what's going on right there. For an instant in time, as this flute passes this quadrant, right at the 90-degree quadrant, The effective rotational velocity, as it applies in the equation, the ratio of rotational velocity to forward velocity, becomes zero for a moment in time. But we still have forward velocity on the tool. Therefore, at this instant, that pressure vector flips to the outside. Now, it's just an instantaneous moment. It comes back in once the flute passes the quadrant. But that creates a huge harmonic vibration. Okay? It also does something else that we want to talk about. It changes the force that is applied to the flute. Now, the desired force is compression force, because carbide is a very hard substance. It's very abrasion resistant, and it can stand up to compression force better than most other materials on the planet. What it doesn't handle very well is tensile force. Okay? And let's talk about that a little bit. If this pressure vector is aligned with the tangency of this flute as it travels through this region where plastic deformation is occurring, as long as that pressure vector remains very, very near tangent to the curvature of that flute, then the only thing it's going to see is this compressive force. But at that 90-degree quadrant where that thing flips to the outside, it's seeing pure tensile, pure tension force against it. And this creates microchipping in the carbide substrate. Now, in general, I would say you can't avoid microchipping. It is going to occur. It's just the way it is. But if you can minimize it and you can delay its start, then you can increase the life of the tool dramatically. And we do this by making sure that we're never violating the maximum cutting angle of 80 degrees. Now, we did some studies on this, we looked at it, and you begin to see an acceleration in vibration, in harmonic vibration, above 85 degrees. You don't see much of it up to about 80 degrees. And so we kind of determined that's the area where that vector begins to start sweeping to the outside, and we wanted to stay away from that. There's not a lot going on between 80 and 85 as far as, performance and productive work. So it was better just to keep the tool down at 80 and keep it in a very smooth and very clean area and not have that vibration. Now, we also don't want to go below 10 degrees, because below 10 degrees you tend to bounce off of the material, especially in harder materials, and you can cause burnishing. So again, one of the areas where we can manage harder materials better than anybody else is that we can increase this minimum angle up into 15 or 20 degrees, where we know that tool is actually breaching the surface, getting under and chiseling the material up. It's not bouncing off the top and burnishing the sharp edge of the tool. So there's a lot of different things in here that are happening that give us pretty excellent control over what we're trying to accomplish. So we talked a little bit earlier about how iMachining can perform really, really high performance toolpaths. You've seen some video of that. There's another area that I'd like to talk about that is not very often discussed, and it has to do with older machines. Another area of concern for people. We've got a lot of customers that have older equipment, and they're not going to replace them. And so we also discovered in our quest for the high performance, we discovered that we can make low performance machines perform significantly better than they've ever performed before. This is a great example. Now, this is one of our customers up in Colorado, and they had a Haas TM2, a tool room, open bed tool room machine. They were cutting pockets very similar to this in their parts that are 1 inch deep. And they're using a 3/8 inch OSG exocarb cutter, pretty good cutter. But they were only getting one pocket per tool, okay? And that's because with this machine, it's pretty rickety. It's not super stable. This is only a 4,000 RPM spindle, and the controller could only manage about 50 inches a minute before it started getting into data saturation. So this pocket, he had to cut at 50 thousandths depths of cut. At 2,200 RPM, and 18 inches a minute was the fastest he could go without creating so much stress on the column that it vibrated things so bad that it was just chipping up the tool, just tearing it up. And so this pocket took him 2 hours and 26 minutes cycle time to cut it. And by the time he got to the bottom, he'd pretty much destroyed the bottom 50 thousandths of that tool. And he had to put a new tool in here to finish the walls. And then he would use that new tool to start the next pocket. So he was basically getting one pocket per tool. So his tooling cost was fairly big. Notice I'm cutting all the way at full depth, 1 inch depth of cut on a 3/8 inch end mill. That's greater than 2 times the diameter. Again, we only have a 4,000 RPM or 4,500 RPM spindle, but I'm using all 4,500 RPM. This machine will only give us 50 inches a minute travel before it starts hesitating. You can actually see it hesitating just a little bit in here. I'm pushing the limit of that. Okay, but let's go ahead and advance this forward. All right. When we get down here to the end of the cut, notice the chip color is just absolutely beautiful. Okay. And as we pull off of this, we're looking at 7 minutes and 26 seconds cycle time instead of 2 hours and 26 minutes over here. The other thing that was really crazy about this, we pulled this tool out and looked at it under a scope, and you could not tell it was a used tool. I mean, it looked brand new. There wasn't even scuffing of the coating inside the chip ejection galley. We ran 3 more pockets on here for a total of 4 on this tool. And that tool was still razor sharp, had about a 5/1000 shine mark down the sharp edges of the flutes where the coating had been kind of abraded away a little bit. But now, if you're familiar with the OSG tool, they have corner chamfers, not corner radiuses, on the end of the tool. So that means there's 2 corners there. Well, those 2 corners of the chamfer weren't even discolored yet. That's after 4 cuts. All right. He was only getting 1 pocket per tool. We got 4 pockets on our test cut without even making the tool sweat. How many could we have got? I don't really know. Probably in the neighborhood of 8 to 10. But he was only getting 1 here, and his cycle time was 2 hours 26 minutes. Our cycle time was 7 minutes 26 seconds. So significant improvement, even on an old low performance machine. Saved them lots and lots of money. Check us out on www.solidcam.com, and one of the things to really point you towards is this star right here. If you'll hit that star, it'll take you into our reviews area. And you'll find we've got over 400 reviews now. And out of 5 stars possible, I believe we're holding somewhere near a 4.92 or something like that. So take a read through some of those the reviews and see what you think. You're going to see a lot of things in there about service and customer service as well as product quality. Also, we have a whole slew of iMachining success stories in here where you can go in and you can read what customers have said about the performance of the systems that they used to use versus the performance of iMachining. There really is a significant difference.
My hopes is that not too many people learn about iMachining because it is my biggest competitive edge.
Okay, so that concludes what we're presenting today. We're ready to go into a question and answer session. So I'll hand it back over to our team from Modern Machine Shop, and let's open it up for questions and answers. Thank you.
Ken, we do have a couple questions that have come in. I know you're at East Tech. Can you hear me?
I can. Can you still hear me?
Yep. Okay, so a couple
Okay,
questions.
great.
One, the 80% rule for tool engagement, how broadly does that apply? Is that a universal application, or is that only in certain higher demand cuts?
The 80-degree limit is really there to keep it from going into that zone where the harmonic vibration starts, and of course at 90 where you get that vector flip. What we really know is that the harder the material, and in many cases, the tougher the material. Those are actually two different things. The lower the maximum cutting angle needs to be because of the heat generation time that occurs in those. And that's sort of a balancing act that you can play. So like for instance, when I'm cutting aluminum, I can use pretty much all the way up to the 80 degrees without any difficulty at all. If I'm cutting in titanium, I typically bring it down around 35 to 40 degrees. If I'm cutting in, D2 or similar hardened tool steels that range, up into that 45 to 52 Rockwell C, sometimes I'll bring that down even lower, like to 30 degrees.
Next question. How much maximum machine load is used in iMachining in terms of percent machine load?
That's kind of up to the user. The default settings, if you just go like I showed earlier in here where I was using the auto settings and you use the actual out-of-the-box condition of iMachining, it's only going to run between 17 and about 22% spindle load is what it's designed to target. Now, if you go in and you make adjustments to those data structures and you start dialing them up and increasing them, you can really put it where you want to put it. My personal preference and what I've done for many, many years is I try to target between 40 and 60% spindle load as a maximum. And that way I'm never damaging the spindle, I'm never hurting the machine, and yet I'm getting extreme performance out of it.
This audience member asks, where can I learn more about the tool cutting physics that you mentioned in the presentation?
Actually just connect with us and we can talk a little bit more about it and maybe even, there's a lot of information out on the web when you start getting into any studies on chip thinning. A lot of them will talk about force dynamics. We've done a lot of study over the last years, practical type examinations where we're actually studying things at the machine, and that's pretty much where we've learned it.
Next question, in what workpiece material does iMachining work best?
That's a tough question because it really works fantastic in virtually any material you throw at it. When you compare it to a traditional style offset racetrack type pocketing operation for material removal, it just improves the productivity of whatever it is you're cutting. We tend to see, I think it's a higher percentage gain in the moderate to tough or hard materials. I think that's going to be where you're going to see it a lot, like for instance the titaniums and the Inconels. Those materials are really hard to get good performance out of a tool, and they're very, very damaging to the tool. With iMachining, one of the biggest things we see in those materials like titaniums and Inconels and such is that the tool life goes up more dramatically than it would, for instance, in an aluminum. Okay.
Ken, this one's a basic question, so step back a little, but the audience member simply asks, why is constant chip thickness good?
Well, if you think about what we talked about with the physics there that's going on with it, the constant chip thickness means that the latent energy of plastic deformation is going to remain very, very stable, which means the force load against the tool in the machine is not going to be variable. And so if you look at carbide, especially the premium carbides that we see today in the tooling industry, they don't handle shock, whether it's a vibrational shock, whether it's a thermal shock, or whether it's an impact shock. They don't handle that well at all. And so if we can minimize that shock we improve tool life, we improve performance very well.
This one's kind of an open question, but it says, what about handling very small tools? So can you speak to small tools, Ken?
Yeah, one of the tough parts about small tools is they're pretty delicate. So if you bury a small tool into a corner with a traditional style pocket, or even some of these other high efficiency pockets that just use constant step over or constant radial step over, once that linear force load goes up on that tool and you start getting that deflective force to it, the small diameter tools just don't have the ability to stand that, and they just snap right off. With iMachining, because we're maintaining that constant chip load and we're minimizing any linear or lateral load force on the tool, it's only seeing really rotary torsional force. Those smaller tools will last significantly longer.
This question is from a machining instructor. He says, is there an educational version of the CAM software, and is there documentation that can be given to students for better understanding the physics of this type of toolpath?
There is definitely educational software available. If he could connect with us on our website, we have a director of educational, Victoria Bremkamp, and she can connect him up with the software as well as with curriculum. And we do have a little bit of documentation on some of this advanced stuff in iMachining that we can also help him out with.
This question sort of asks for clarification on some of what you said about thin wall machining. The question asks, basically, what do you mean by good thin wall handling in iMachining?
Well, one of the things that happens, anybody that's been in, especially like the aerospace industry where they're working on bulkhead frames and stuff like that, when you begin machining against thin walls, you tend to create a lot of stress in the body, and when you unclamp it, things tend to warp and change, and it gets pretty tough. One of the things about iMachining, because we're not applying a linear force to the material, and because the way we are removing the chip in such a consistent manner deflects all the heat out with the chip, we're not putting work-induced forces into those thin walls and thin floors. And so in many cases, when you unclamp that part after machining, it's not warping real bad at all. In a lot of cases, it doesn't warp at all. In some cases, the warpage is so minimized that some simple straightening or some simple vibration stress relief completely resolves the problem, versus if you're doing high force load type machining in those type of conditions, you can wind up having rib walls that deflect down the line of the rib wall that need to be straightened.
This question asks, what's the rule for selecting the ideal iMachining level? Do you pick low and try to go higher, or is there a better approach to picking the optimal level from the first try?
Good question. Sometimes it is what you experience on the floor with it at the machine. A lot of what the level slider is there for is to manage tool extension, fixture instability, things of that nature that are not predictable ahead of time. Okay. I tend to also use it to minimize spindle load. If I program something, for level 8 being 40% or 50% spindle load, and it turns out when I get out on the machine that it's running a little higher, like 65%, a lot of times I'll just go back in and drop the level slider down one notch and repost the code and put it on the machine, and we're off and running.
This question says, what do you use for finishing after using 3D iMachining for roughing?
We've got a lot of different options in the software for finishing. We have our HSM, which is the high-speed machining module, which has, I think it's like 12 or 15 different strategies for approaching finishing toolpaths. And that is the selection of which one you're going to use there a lot of times depends on what the aesthetic requirements are for the finished product. If you need alignment of tool lines or things of that nature, you can choose some of our 3D corner offset or Z-level machining, whatever you need to do. But we have some pretty significantly fantastic finishing operations as well.
Next question, how efficient is 3D iMachining for multi-pocket prismatic parts?
Extremely efficient. 3D allows it to basically automatically look, I guess I should say this first. In 2D, iMachining 2D, as I said in the presentation, leaves all of the ordering, the chronological ordering of which sections get machined when up to the user. So if you have a particular reason that you want to, for instance, I want to work a center pocket, and then I want to work an outer pocket, then I want to work a transitional pocket, then you can do that with 2D very effectively by simply picking them in the order that you want them to run. In 3D, 3D is going to automatically manage a really nice ordering solution, but it's also going to include depths. So if you have multiple pockets in different regions that are at different depths, it's going to automatically pick up all of that as well. Whereas 2D, you would have to do a different operation for a different depth.
A couple more questions. This one's pretty open-ended. In what direction are you going with new iMachining developments?
I think probably the easiest way to answer that is we are always trying to find more areas where we can take advantage of the technology that we're learning. One of those going forward is our eye-turning, where we are looking at being more effective with chip removal in a turning operation, where we're stabilizing the force on that as well, so we're not seeing the type of deflections that you see in normal turning operations. And we're able to more effectively clear out areas of roughing than we would otherwise be able to do with standard or traditional type turning operations. Also taking advantage of newer insert geometries and things like that that capitalize on some of the science of chip thinning.
This one, I believe, will be the last question. It says, does iMachining pay attention to the maximum work feed of the machine to calculate depth of cut and radial engagement? Specifically, if I need to repost a toolpath from a fast machine to an older one, can I get a good cutting parameter there also?
Remember that iMachining is taking into account the machine kinematics. So when you set up your machine definition, if you set that up correctly, then yes, if you switch machines, you simply recalculate the iMachining toolpath, and the iMachining wizard will take that new data into account, and it will reestablish that set of parameters for first part success.
All right, that'll do it. That concludes today's webinar.
Okay.
Thank you, Ken Merritt of SolidCAM.
Well, thank you. Appreciate being here, and sorry for the background noise. But we're up here at East Tech, and we're going to be showing things how it's done up here.
The background noise is good. It's good to be people out at events again. So to our audience
Yes, it
members,
is. It is.
to our audience members, thank you for your time. Learn more at solidcam.com. An email with a link to a recording of this webinar should come to you soon. Thanks for your time today. Again, I'm Pete Zielinski with Modern Machine Shop Magazine.
Thank you all. Have a great day.